My name is Mohit and I am presenting the CS523 final project, that is probabilistic probability testing, and the objective is to compare Solovay, Stressen and Miller-Robin for fast probability testing, implement both from scratch, list early pseudo-primes each test accepts, measure empirical error versus round K on random odd composites. Key question: how fast does error drop? And which test is stronger in practice? Abstract: we implement two probabilistic probability tests, Sullivan-Stressen and Miller-Rabin, and compare theory with practice. SS uses Euler-Jacobi criterion, MR uses strong witnesses. We measure empirical false positives rates versus number of rounds and list pseudoprimes that fool fixed bases. Results match the bounds 2 to the power minus k of SS and 4 to the power minus k of MR, with MR typically stronger per round. Methods if we see in one slide are implement Jacobi SS MR in Maple, use Maple only for helpers, that is random S prime plotting, and two experiments, that is pseudoprimes under a bound and empirical failure rate on random odd composite in A, B for k from 1 to k max. Use randomize 5 to 3 for reproducibility and plot log 10 failure and overlay theory lines, that is 2 to the power minus k, 4 to the power minus k. And here we import the required, that is the default libraries, that is plots, random tools, num theory, etc. We need two building blocks that everything depends on, that is Baumod and fast modular exponentiation, binary powering, IGCD, that is iterative GCD. These make the test both correct and efficient. And these are some utility functions. Along with that, there is Jacobi symbol that generalizes the Legendre symbol to composite odd n. SS uses Euler's criterion with Jacobi A, n as the expected value. Mismatch is a witness of compositeness. We implement a standard iterative algorithm with quadratic reciprocity. SS intuition. SS in one line, if we say, is compare x a to the power n minus 1 by 2 mod n to a by n map to 1 to n minus 1. A mismatch is a witness which implies composite. Over k random basis, error less than equal to 2 to the power minus k. And here the Jacobi function is there. And if we talk about the Solovay-Stressen's idea, for k random bases belonging to 2 to the power n 2, 2 to the n minus 2, compute x is equal to a to the power n minus 1 by 2 mod n and the Jacobi A, n. If they disagree modulo n, we have found witness, which implies composite. If no witness appears in k rounds, return probably prime. Theory gives error less than equal to 2 to the power minus k, and the Solovay-Stressen implementation is below. If we talk about Miller-Rabin, the idea, write n minus 1 is equal to 2 to the power s into d with d odd. For base, a test if x is equal to a to the power d mod n is 1 or minus 1. Otherwise, square up to s minus 1 times to see if you ever hit minus 1. If not, a is a strong witness, composite. At most, 1 by 4 of bases are strong liars, so error less than equal to 4 to the power minus k over k rounds. Miller-Rabin, basically 1 round, k rounds and fixed bases. MR intuition. MR in one line, write n minus 1 is equal to 2 to the power s multiplied by d if a to the power d not equal to 1 and repeated square never hits minus 1 mod n. And a is a strong witness which implies composite. At most 1 by 4 bases are liars, so error less than equal to 4 to the power minus k after k rounds. And here the MR 1 round and related Miller-Rabin is implemented. If we talk about the helpers, what we will measure: two utilities for the components, find pseudoprimes, first m odd composites under a bound p that the test wrongly accepts, and failure rate, failure curve, estimate empirical error on random odd composites in A, B as k grows, single round SS and fixed base finder. And here are some implementations of single round find base pseudo primes and find base pseudo primes MR. Then how to rate this? The less randomized SS may show a few false positives at small k. Randomized MR often shows none in this range. Fixed base lists, bases 2 by 3, are the classic pseudo-primes and help explain single base failures. Experiment A pseudo-primes. What to say? We now list 20 earliest pseudo-primes under b is equal to 2 lakh for each test at k is equal to 3. These are composites that slip through. Small lists are fine. Goal is illustrative, not exhaustive. And some helpers are there. And along with that, if we see about the plot, reading the plot, we show log 10 failure versus k for SS and MR with theory lines 2 to the power minus k and 4 to the power minus k. Points on the floor mean no failure observed at that sampling, consisting with very small true error. MR slope is steeper, matching 4 to the power minus k. Experiment B is error versus rounds k. And if we talk about how to reading this experiment, we estimate the empirical failure rate for k is equal to 1 to the 8 on random odd composites, that is 10 to the power 5, 2 to the power 2 into 10 to the power 5 with 200 trials per k. We plot log 10 failure using log 10 from init box. So exponential decay looks roughly linear. Expectation MR decreases faster than SS as k grows. And here is the code for failure curves plus plot, which results in a plot that we can see here, empirical and theoretical log 10 failure versus k, odd composites in 10,000 and 20,000. So here we can see the plot. And if we talk about 64-bit determinism context, fixed bases libraries often use small published base sets to make MR deterministic for all 64-bit n. Here we demonstrate the idea with an illustrative base set site standard for exact sets. Fixed bases, that is determinism on 64-bit. In practice, Miller-Rabin can be made deterministic for all 64-bit integers by testing a small fixed set of bases as documented in standard interface references. In this worksheet, we demonstrate the idea using a tiny base set. In your write up side the course notes paper for specific base lists and theorems, the exact bases you use here are illustrated. So if fixed basis demo, we can see here, as we can see the results are true, true, false, and some big numbers and true, false. And if we talk about results, takeaways, and sources, results both test empirical failures rates drop rapidly with the failure of rounds k. Miller-Robin falls faster than Solovay-Streisand, consistent with the bounds 4 to the power minus k and 2 to the power minus k. In our randomized trials, MR often had no observed failures in range of modest k, while fixed base lists showed classic pseudo-primes for single bases. Takeaways are that MR is greater than equal to SS in practice, stronger per round and widely used. With fixed bases, MR is effectively deterministic on machine size integers. Use base sets from the literature. A typical production flow is small trial division, a few MR rounds, or fixed bases except. So here are the references which are related to coursework and a research paper. And thank you for watching.